Now we have the next invited talk by Vicki from Johns Hopkins Applied Physics Laboratory.
Hi, thanks for having me here. I'm really excited to be a part of this workshop and some great talks already. So today I'm going to talk from the aspect of putting some of these algorithms on board and how do we move towards that. In particular, can we start designing from the ground up with these constraints? And I want to thank my collaborators at APL and SWARE as well. So if you only take one thing away from this talk, it's that the path to onboard AI starts with constraints, not afterthoughts. And this basically means we need to put those onboard constraints at the very front of our evaluation of algorithms, at the very beginning of our testing, instead of at the very end where we fully validate it on process data and then try to force it into these very narrow onboard constraints. So why put AI on board? Well, Maria Federica mentioned some of these reasons, but the main thing is you should only put AI on board if the use case requires it. There is so much pushback to put these types of models on. And so you have to have a strong case that either enables the science, creates new opportunities, or other things like that. One of these reasons is that we're generating an exponential rate of data in heliophysics across a lot of different sciences, a lot of different fields. You can see that SDO has this massive amount of data. Each individual mission is adding more and more, but our downlink capabilities are not growing at that exponential rate, and that probably in the near-term future or a little beyond that, we're going to have to start thinking about how do we make intelligent decisions on which types of data to downlink in order to enable science to be done effectively with these new sensing technologies generating so much data. Another reason we might want to put AI on board is we want to make decisions on board because, say, we have a transient event and there's not enough time to downlink the data, run our processing tools, and then uplink our observational schedule changes. So AI can be an enabler for fast transitions in observation modes, and particularly this might be of use in space weather hazard safety precautions. So with onboard AI comes a variety of constraints. And the big gorilla in the room is compute, memory, and power. So to demonstrate this, I take 3 different types of processors. The first is a Leon 3 processor. This is being flown on several missions, Parker Solar Probe. It's kind of a legacy processor. It has a moderate amount of CPU, no GPU, but its real strength is it has less than 1.5 watts to run basically an entire instrument. It's very robust. If we compare against what we can run sort of on my laptop, like an Apple M1 chip, compute power is getting pretty good on a local laptop, being able to at least run most algorithms. We have a lot of CPU, a vast amount of GPU, but because it's plugged into the ground, we don't really care about power. So we're at like 20 to 30 watts to average on this processor. Then if we move to sort of the state-of-the-art space processors, they're starting to resemble our laptop capabilities. It's not high-performance computing, but there's really expansive GPUs. There's a fair amount of CPU and storage and memory, but at this very high cost of 20 to 40 watts in comparison to 1.5 watts, which is running an entire instrument. So to put this in context, for the ESA Vigil mission that's coming on in the next decade or so, the spacecraft has 1,200 watts with its solar power arrays, but only 200 of those watts are allocated to the payload across 6 or potentially more instruments. So that's not a lot of power. So if you have all these algorithms that are very power hungry, they have to share amongst the other instrument capabilities. Some other challenges for onboard AI are that the majority of our methods or algorithms that we're testing on the ground on process data, calibrated data. When we're up on the mission, we have raw data. The calibration is typically done almost entirely on the ground. Pushing that type of processing aboard is very computationally expensive, so it has to be done for a reason. And a lot of those methods are not tested on those raw data or considering what that raw data is looking like. And these models have to be fast, lightweight, and robust for obvious reasons to fit into these constraints. So today I'm going to talk about 2 case studies of some work that I've been doing. Case study one is the typical paradigm. You have a lot of collected data. It's already calibrated and processed, sitting there in a nice box. And you choose an algorithm that best fits that data. And then afterwards, see how you apply it on board. Case study 2, we sort of flip the entire paradigm. We think of onboard constraints first and foremost, and we build up the model from simplest to complex to fit within those onboard constraints, and not trying to have the best algorithm out there, just one that fits within parameters. And so throughout that process, we also have to keep in mind the raw unprocessed data that it would likely be evaluated on. So case study 1 is what we've heard a couple times today from Silvo and Ramon about identifying plasma regions. So we are using MMS data, and MMS is a 4-probe spacecraft that is looking at the Earth's magnetosphere. And in particular, we're interested in looking at some of these transitions between plasma regimes like bow shocks and magnetopause. So as it's done now, the data is taken in 2 modes, high fidelity and low fidelity. You cannot transfer all the high fidelity data down. It's simply downlink constrained. So what's done, and what Ramon had mentioned, is there's humans in the loop. We call them scientists in the loop sittles. And they are given a quick look view, and then those humans have to go tag the most important data to downlink. And so that requires a person. Someone's always on call throughout the lifetime of the mission. It is subject to human variability. One scientist may think this type of data is more important than the other. Someone might be tired, not want to be on shift, and miss things that are very important to others. So a potential reason for a different solution is that we might want automated solutions in situ. So our team came up with a unsupervised learning method using Gaussian mixture models. And Gaussian mixture models is well suited for this type of data because we knew how many clusters we wanted to identify. We wanted solar wind, ion foreshock, magnetosheath, and magnetosphere. And then we built up features that could really accentuate those clusters. We tested it against Siddle transitions, so we validated this data. You can see in the middle that actually this Siddle didn't actually capture the bow shock. So there are variabilities in how Siddles are evaluating. And then we also validated against the manually labeled Olszewski et al. 2021 data for their 2 months of 1 minute cadence evaluations. And we had about a 98% match rate with that. We also have some post-cleaning methods alongside to remove things that don't make physical sense, like magnetosphere to solar wind. Once we were happy with that, we applied that model to 8 years worth of MMS dayside data. And then we went one step further and we took that model that was sort of tuned on Earth-based data using MMS, and we tweaked some of those normalization knobs, some of those post-cleaning models, and we applied it to a less data-rich environment that's Mercury's messenger data, and we applied it to 4 years of dayside data. So once we have the model that we are fairly confident with, how do we think about getting it on board? How do we get it on existing spacecraft? Well, you basically can't. The compute is fully capitalized for most missions, and they're running things like a Leon 3 or something that is farther in the past that can't actually take some of these methods on it. We also did not validate our data on level 0 data. It was all on calibrated process data. So there could be a lot of drastic differences from our validated process data against raw data. And if we're doing post-cleaning methods, those float calculations can be very costly. And so they can greatly blow up our computational budget. So if we look to the future, how could we potentially get this on board new spacecraft? Well, we chose our model based off of what we have in front of us, and it's well suited for that. The Gaussian mixture model is not commonly put on an FPGA, so you would have to come up with a custom solution. You would need to think about how do you update this model from early mission life cycle, where there's very sparse data, to a late mission life cycle where there's an abundance of data. You have to think about how much do I need to train? How often do I need to retrain? And do I need sort of a hybrid model in between where there's something more simple in the beginning and we expand out to our most complex version? There's also a lack of trust in the system. Do we have proxy data that fits our new mission? Because every mission has different instrumentation, different capabilities. And then finally, you're going to get the question, why can't we just do this on the ground? It's less risky to put it on the ground. In this case, we might be able to. We might be able to just automate the SITL process and tag them and then send up, we want these specific time windows. So if we think about case study 2, looking at solar flares, we've heard Enrico talk about this is a very rich area for machine learning. So we want to potentially study the precursors of solar flares, get them right as they're erupting in solar dynamics observatory data. So how is it done now? We take tons of temporal data, and then once we know when a solar event is happening, we can study a specific window in depth because that data is very dense. And then there are also lots of various forecasting models out there. The problem with that observation scheme is that you cannot change your observation mode. It only gives you higher resolution, either temporal or spatial. It doesn't actually allow you to, for instance, put an aperture or something else when you want to look at the event before it's occurring. So this leads to a potential solution to automate real-time decision making. So we came up with an algorithm. I will preface it that this is a computer vision algorithm, but it helps us understand some of the constraints on AI on board. So we use 7 EUV filters from SVO AIA, and we do some frame subtraction. We have macro pixels that are just an 8x8 grid, and we trigger when one of those macro pixels in 304 angstrom is above some threshold. And then on that particular macro pixel, we take a bunch of ratios for EUV filters and use computer vision to find a particular signature that we think is associated with the pre-flare. What is unique with this study is that we designed it for onboard in mind from the very beginning. We actually started with the simplest method that we could do, which is one EUV filter with computer vision. Did not find good results. We expanded out to one EUV filter with more modern machine learning methods using things like long short-term memory neural networks, and then we baseline those against random forest. Did not get good results. Then we moved towards this method and found something that might be of interest. So there are a lot of considerations that went into developing this algorithm. One is we do background subtraction. We take 4 hours prior from every observation, the median of the entire solar disk. And so we can subtract that to try to remove long-term degradation across detectors and biases that we would not have with the raw data. We use a standard grid. You would consider it would be better to have a dynamic window around an active region where there might be a solar flare because it would fully encompass the region of interest, but that is computationally expensive. So if you sort of fix that grid, you can reduce those expenses. And then we also spatially downsample. So we're only having to carry along 64 macro pixels. We are looking for this very narrow, coherent peak in our ratios that basically just take advantage of means and ratios, which are computationally inexpensive to other methods. We take the ML-ready temporal cadence of 6 minutes because if it's working for that data set, we don't need to carry around 1/30th of the raw buffer alongside us. So we can calculate this every 6 minutes instead of every 12 seconds like SDO does. And then we consider how do we reset our buffer. So when our trigger goes on, how long do we have to keep that data? How long do we have to keep running those calculations? So I'll jump right into the performance results. So we tested this on roughly 2,600 GOES flares that were C1.0 and higher. And we have a detection rate of close to 70% and a false positive upper limit of 35%. The upper limit is because when we visually inspected, we saw that some of these were associated with lower class flares or potentially regions that looked like they might be interconnected. And then we took this nice paper by Lecca et al. 2019, where they took 19 operational solar flare forecasting models. They applied them to the same data set using the same metrics. So it's an apples to apples comparison. These operational models span the gamut of modern leading edge AI models to human in the loop or human identification. And so in the middle is the 11 operational models that had forecasting for C1.0 and higher within 24 hours. And our results are the upper limits shown in the red triangles. So we have some comparable results with these existing models, same with the accuracy and true skill statistic. And actually within the similar interval that Lecca et al. Chose, we didn't have the exact same data set. We were truncated by about a few months. We had something closer to 75% detection rate. So we also considered the timing of the detection that I sort of teased before about the buffer. You saw with the pre-flare signature, we sometimes get multiple of those signatures. What we found is if you take the latest signature and you hold it in the buffer for 160 minutes at that 6-minute cadence, you can recover 80% of the detected flares. So you don't have to keep an infinite buffer forever. And we can take a lot of lessons away from this study, even though it is not AI, it is computer vision. That is that we should start with constraints, think about them because they can really evolve how our design goes. That the main knowledge of the types of data we're looking at can actually sometimes reduce the complexity, and that we have to consider these very strong levers on our computational costs of the trigger logic. What do we always have to look for? And what are we always having to compute? And then once that trigger is gone up, what do we have to spend our more expensive computational time, and how long do we have to keep that buffer going? And that these sort of simpler algorithms can rival some state-of-the-art models. So overall, if we look towards the path of AI on board spacecraft, we have to anchor it in a use case. AI should only be used on board if it is necessary and is bringing more value to the mission. We should think about flipping the paradigm of building the best model and then trying to fit it into this small computational box, and instead step back and think about the observational constraints first while we're designing the model and while we are validating it. So some ways to do that is to choose the simplest method that works rather than the best method overall. Incorporate what the raw level 0 data is going to look like into the beginning of the design so that you don't have to go back and say, I needed a lot more compute because I have to have the fully calibrated pipeline. Build trust by validating both on the level 0 and the level 2 data to show that you know it's going to work if it's put on board, and really identify a data set that you can validate on, either a proxy data set or synthetic data set that is going to model what is going to be seen on that mission. We also need to really think about mission evolution. We have these really robust models, but they are tested after you've accumulated a ton of data. What do these models look like in early mission life cycle? In late mission cycle, we have tons of data. How much data is actually required to train a new model, and how often should we train them? So then we would consider maybe we have a hybrid model. Maybe we have very simple thresholds, humans in the loop in the beginning. We've built out for these computational constraints for later in the mission. How do we uplink a new model? How often do we uplink a new model? Do we need to put onboard training on board, or can we do it all on the ground and just uplink as we need it? So if we look towards actually getting on a mission, we first need to identify a use case that strongly requires these types of heavy compute algorithms. We need to identify next-gen mission constraints. We need to identify a proxy dataset for that mission so that we can test and validate on, and then build a simplest working model, apply it on a more constrained platform to show that we can do it, and then build out contingency plans. And then we can potentially propose to a next-gen mission like the heliophysics links. So if none of that came through, the main takeaway is that think about onboard constraints much earlier in the process. And thank you for your.
Okay, questions.
Yeah, a couple of quick questions. So the first is, I didn't quite understand your solar flare case study. How makes it onboard specific rather than, I mean, in other words, why that whole pipeline you described cannot be done on the ground? So the first question. The second one maybe kind of challenges this TLDR, because my maybe ignorant understanding of just following all the discussion about onboarding AI, which have been going on for like 10 years or so, is that we're not going to use, I mean, the whole thing that you showed is how to use, I mean, how to adjust to those constraints, not use the CPU with the least computational cost possible and so on. But those CPUs, I mean, and GPUs, those are general purpose units. If we're going to onboard, say, a neural network, what we're going to do is to design one, I mean, call it CPU for the lack of a better term. It can only do that one thing. It can only execute a predefined neural network, and that's going to be super cheap. So it's kind of going to throw away all the constraints you're talking about, because it's a different framework. You see, it's now we know that we need this neural network with 10 million parameters, and we're going to design a chip that can only do that thing. It doesn't know how to do anything else, and that's very, very computationally inexpensive.
Yeah, so for the first part of your question, why does our model, why can't it be done on the ground? Since we use the 7 filters and we need a long period of time actually downlinking that amount of data and processing it, not,
But it is being downlinked, right?
it is being downlinked, but not at a high cadence so this is within like the 4 hours. It doesn't downlink all that data and go through the.
I mean, this is kind of a hypothetical scenario you're talking about. I mean, SDO downlinks data every 12 seconds.
Yeah, but it's not being able to, like, we are not processing all that to keep. So, I mean, if we are getting it in exactly 12 seconds, we can potentially do it on board, right? Because we have potentially a 4-hour window that we can then give it a command to switch observation modes. So you're right in that respect. We're thinking on, we want to be able to do it quickly, putting it in that ground-based pipeline is not really being done right now, right? We haven't evaluated that in real time. If you can do it, what's the latency? For the second part of your question about if you have built a neural network that is well designed for the constraint, the actual hardware that's being flown right now, they don't take into those considerations. There has to be a reason to put the larger compute, right? Like, how much power does it take to run a neural network? And how much is that relative to how much an entire instrument is running right now? Those are the types of things that the hardware and instrument folks are really pushing back on. Like, do I really need these more expansive processors? Do I need these more expensive FPGAs? Like, we have to bring them up into TRL. We have to do all these things. And then that is assuming you know perfectly what your data is going to look like in late stage of the mission. You might want it to evolve and not be constrained to that one specific type of neural network. You might want another layer, things like that.
Go ahead.
Yeah, so I also have 2 questions. So one related to the flare detection tool. So you mentioned it's a computer vision algorithm. What type of algorithm is it, and how does it compare to the SOFAST algorithm? That's
Yeah. So SOFAST does a lot of this component where they're looking for, they're doing background subtraction, they're doing a trigger. We are looking for this specific type of peak. And so we're looking for a coherent peak and everything related to 94 angstrom. And then we have some filtering based off of these 2 other ratios. So it's the actual signature that's different from SOFAST.
Okay, but it would be used in the same way, I guess, right? That's the idea. Like on a mission like Solar Orbiter type mission. Yeah. Okay. And my second question was about the GMMs, because you mentioned that it's difficult to, they are expensive to train. And I was wondering if you actually need to train them on board, or you would just use those centroids to just infer. But if you just need to run it inference mode, then maybe it's not so expensive to use them after all on board.
I never would advocate for anyone training on board because it just doesn't make sense. You should train using your infinite resources on the ground and put the inference on. More of it was more on the inference is not commonly put on FPGAs as far as I know.
Yeah, that's correct.
And so You actually have to probably build a custom solution.
But, or we could put it into a CPU, or maybe, I don't know, like, I have no idea how
I mean,
much it would
training
consume.
on
but
board, I mean, that's almost
Yeah,
it's
yeah.
a circular argument. You want to train on board because you don't know what data is coming, right? If you already train on known data, I mean, that's the argument you made. I mean, we fly new missions because we want
Well,
to
I guess
discover
we would
stuff that we didn't
train
know
on the
about.
burst mode, and then we would, that does get
I
down.
mean, you want to train on the
Well-
data that then possibly you're not downloading because
But there, maybe there is no like a supervision, so you are a bit worried that the algorithm is, I don't know. Like,
The non-calibrated data might look very, very different than the calibrated data.
yeah,
So I was wondering if you have, because if you look at a certain interval of non-calibrated data, and then you calibrate them, would you be able to do some kind of a scaling?
That is what we are trying to propose, because we want to do this. And see if it actually works on a level 0 data, or if we can actually make some modifications to do it, to prove out that this might be a viable method. But so far, it's been hard to get the level 0 data, and it's been hard to get the money to do the analysis.
Because I would expect that the fluctuations in the level 0 data are much larger than
Yes.
calibrated. So
Exactly. So I would think that this is like a strong reason maybe to push it to the ground because you're taking some of this data already into fidelity modes.
Do you have an idea? So first, thank you for the talk. It's very interesting. And do you have an idea of what inference latency those models have to meet on space? So when you design a model for space in the hardware perspective, when you make a hardware, when you run them, you need to meet a certain inference or the cadence of the inputs. Do you have?
Yeah, I don't quite know the timing scale of that. The real problem is typically on board spacecraft, you're already ripping it up for different packets, right? So it's to reassemble the data before it's or intervene before it's disassembled. I don't know what the inference is, and if it is on the same timescale of the rest of the instrument that it would.
And regarding the unsupervised, if you don't run the unsupervised on board, wouldn't you have to send the data all down to Earth? Wouldn't that?
You could potentially send down what's being sent down for SITL and then run it on that SITL data, because I think it stays for at least a week. The MMS SITL, they're only expected to review every few days. So you could potentially do that where it's the quick look data, where it's not as expansive as the full high fidelity data, and then identify, send it back up, and get those just like replacing a SITL.
Thank you.
let's bring the speaker again.